Hello, welcome back to Jonas Statistics and Mathematics Tutor. Today we are going to embark on a different journey. In our last video, we learned something about how we do data cleaning and its correlation. Today we are going to work with numerical data, how we handle numeric data when we come into contact with it, right? And then when you compare numeric data to qualitative data, you could see that the numeric data is more or less cheaper than the qualitative data, right? So today I'm going to walk you guys through how we use the numeric data when we come into contact with it. And then we are going to use an inbuilt data called CAS, right? CAS. So that's the inbuilt data that we are going to use to do our handling with numerical data. So I've already taught you how we can see CAS in R and how we can also call CAS to work with. So here we are just going to upload what we call our CAS listing. Let me delete this one from there and delete section. So we are going to use section what? So how we can call this one. So once you use the data blah blah will come, right? The data has we have seen the data, so we have the space and the distance, right? So at the end of the day, when the data comes, right, I told you guys that the assembly will give you the central tendency of each of the column, right? So let's use the summary to get all that I will say. So we have it nice here, so for the speed and for the distance, right? We have our minimum, our median, the mean, the first quarter, the second quarter, as you can see down here, right? So at the end of the day, since we have that one, right? So it just giving us an idea about how our data is, right? And we can also go on further to also check the structure of what our data, right? CAS, right? So we can also go on to check the structure of what our data. Once we run to, it's also going to tell us that for the speed and the date, they are all having numerical characters. And then we have what we call the scale and center, right? When you handle numeric data, I have what we call scale and center. So for instance, maybe we really want to, let's say, compare two different variables in a data. But you could see that one variable is, let's say, higher, right? Is having a higher value than the other, right? And you want to compare these values. If you want to compare this variable. So if you really want to compare this variable, you see that it will be very, very difficult for you to give a clear comparison between the two, right? So what we will do here is that we will use the scale and the center to normalize the data in such a way that it will be in a good shape for us to do our comparison. So for us to use the scale and then center to do the normalization, we have what we use, we have this function in R called what? Scale, right? So the function in R called scale, as you can see here on my screen, right? Scale. So for this scale function that we have in R, use that one. So the first argument here will be for what? The data name, right? That's the center. The syntax. The data name, and the second argument will be center is equal to true, and the scale 2 is also equal to true. So once you have center is equal to true and scale is equal to true, everything is done, right? So once you run this one, right? Once you run this, you will see that it has put them into a shape. So right now we are having a similar mean, right? The mean here is 0.00, the mean also here is 0.00, right? We have our median to be 0.075 here to 0.27, and then we have our first quarter. You see the first quarter for the speed and the first quarter for this one too is much more or less similar, right? The minimum too is more or less similar, right? So you can see that it has normalized what our data. So once you see our mean is equal to 0, and then for the two the variables is equal to 0, it means that our data is in good shape for us to do our comparison, right? So that is how the scale and the center functions works. So once you know this one, it will really help us to do more with R, right? So we can compare our variables that we have in R, right? And then secondly, we really want to deal with how we really want to deal with what skill data, right? Sometimes we have what we call parametric approach and non-parametric approach. You see, parametric, we normally use parametric approach when our data is normally what distributed with what our hypothesis testing. But sometimes we cannot use the parametric approach since our data is not normally distributed. So when our data is not normally distributed, we use what we call non-parametric approach. So this non-parametric approach that we usually use that to transform what our data, right? We really use the non-parametric approach to transform our data into what its correct what shape, so that at the end of the day it will hold, right? So at the end of the day, since we are come to plots, right? So I just want to use these options, right, to set the inch for the width and the height, so that it will not be something that is very big like that, right? So at the end of the day, we are saying that the inch for the width is 4, and we are saying that the height for the width, the height also should be in what 4 inch, right? So I don't believe I really want you guys to just generate a data in R, a normal data in R, right? I just want you guys to just generate a normal data in R. So that normal data in R that we have, that when we plot, it will be normally distributed for us to see how a normal distribution curve is how normal distribution curve usually look like, right? So here what we will do is that we use our n is equal to r norm, right, into bracket of what 100,000, right? So R is going to just generate 100,000 individual numbers in R, that when you plot, it will usually the graph will depict what a normal distribution, right? So for you to call a normal distributing data in R, what you use is what the R norm, right? The R norm that we have here, right? The R norm. We have this R norm here that we have. So and then you just put in this one. So once we run, right, we have R norm, we run and then print. It has been given to us over 10,000 variables, right? 100,000 that we have. So we just want to plot this one, right? So creating what histogram of what the distribution. So at the end of the day, you see that we use what we call the hist. It's bracket of what the variable name, right? So here the variable name here is n, right? And the breaks is equal to what 30. So the breaks is equal to 30 is going to take what variables into what 30 what intervals, right? So let's the variable from 0 to 30 will be counted in one what interval, right? So at the end of the day, you just run this one and we see our graph nicely depicting here, right? So you see, this is how our curve look like, right? So this is a typically a normal distribution table, as you can see, right? Normal distribution graph, as you can see, right? This is normally that. So usually they are in the form of what a bell shape, as you can see it here, right? But sometimes you see when you have a typical data and you really want to graph, by the time you realize you grab this data and it will not be normally distributed, and when it is not normally distributed, most of the time you cannot. Some of the machine learning algorithms you cannot use them to model the data, right? So you have to use the non-parametric approach, one way or the other, to transform the data to look like a normal distribution, so that at the end of the day it will help us and aid us in our experiment, right? So I want you guys to also generate a skill data, right? More or less exponential data. You see, exponential data are not usually normally distributed like that, right? Me and you know that exponential data are more or less a continuous probability or distribution data, right? So at the end of the day, it's not normally distributed like that, right? So for you to generate this exponential data, we have what we call the RSP, right? The RESP function, right? And then the syntax is for you to get the so we have RSP into bracket of what? This one will be for n, the number of observation, right? And the 0.5 will be for the mean, right? Or rate, right? As you can see here, the mean of what rate, right? So this 0.5 will be the mean of the rate. As when we want to calculate probability function for the exponential distribution, what we have is what the n. What we are supposed to get is the n and what the mean, right? Yes. So we are going to use this same thing to generate. So it's going to give us 1,000 this thing, right? 1,000 observations. So once we run that one, print k, right? It has given us our 1,000 observation, and we want to plot for you guys to see how they skew it. So when you have skew data, it will either be skewed to the right or skewed to the left, right? So once you run it, right? Sorry. So you see, we have gotten a nice skew data, right? So you see, this one is not skew. This is not a normally distributed table, right? This is what skewed to the right, right? This is skewed to the right data. And if you have a data like this, we cannot use it for our analysis. So we have to transform this data into a normal distribution so that it will aid us to be able to perform our analysis, right? So at the end of the day, what we have to do is that we have to transform our data. And usually, if you really want to transform your data, we can use square root to transform your data. We can use log function to transform your data. We can also even use the non-parametric approach, right, to also transform our data, right? So at the end of the day, we want to use the square root to transform our data. So this k square is what? This k dash sqrt is just this is just a variable name that you have given to the square root. So the square root into bracket of what? The k, right? The k here is what? The exponential table that we just generated, right? That is skewed to the left, right? And then we just plot it using the his, that the variable name, and what the bricks, right? I've already I explained that one in the last plot that we did, so I'll just run it for us to go early, right? So you see, when I apply the square root, you see the data is not normally distributed, but you see it has transformed, right? A little, right? It has transformed nicely, right? It has transformed. See that it's gradually it's looking like a normal distribution, but this is not normally distributed, right? So sometimes you can use the square root. When you use the square root and it will fine, you can continue your studies, right? But when you use the square root and still it doesn't work, you have to also use another distance. So we have log function here, right? So we want to also use the log function to test if the data too will be in a normal distribution. So once we test, and then you see this one too is also, it has also transformed to be more or less a normal distribution, but it's not normally distributed, right? So more or less after we have done this one, at the end of the day, we can also use a format. This is all this our graphical approach for you to detect if the data is normally distributed or not. So we can also use what this is just a graphical approach. You have to use the format test, something like chaperone test. So this chaperone test will also test to detect if the data is normally distributed or not after making a transformation, right? So these are the simple transformation distance that you can use, right? In our subsequent videos to come, you will really use those functions for you guys to see how it is for data to normally distributed, right? So at the end of the day, in our previous videos that we have, I think in section 5 we talked about matrices, right? Yes. So I just want to recap this matrix here because we are going to do correlation analysis next. So we are going to use the idea that we have in matrices to do that, right? So I don't believe you see when you have matrices, for you to be able to store matrices in R, we use what we call the matrix function and what the C function, right? So here I have 9 observations, right? So please, you are going to watch it. Kindly go to section 5 and then watch it, and it will really help you a lot, right? So we have this matrix here, and then we have C here, right? We have what C here, right? The C function here, right? And then n row is equal to 3 and n cow is also equal to 3, right? So once you run it, it's going to give us a nice matrix plot, as you can see here. And then I told you guys that if you really want to, let's say, call a certain row and a certain column in your matrix what data that you have stored in R, we use what we call the variable name, a square bracket, and then the first argument will be for the row and the second argument will be for the column. So as you can see here, but here I just want to call the column. If you really want to call the column, you place where the row part to be what comma, and the column will come here nicely, right? So here we have 2:3, as you can see here, 2:3. So for this 2:3, it means that we are going to call the second and the third row column, as you can see, right? Nicely. So we have called what the second and what the third column, as you can see nicely here, right? So for correlation variables too, I just want to really use the two columns that we have in our car data, right, and just perform a correlation analysis on it. So you see, sometimes you want to really check if a dependent variable and a certain independent variable really correlate. For instance, if you are having a diabetes data, right, and then for diabetes we have a column that will be for dependent and another column that will be for non-dependent, a dependent and another column that will be for independent, right? So we just want to check if the dependent will be like, we want to ask the person, do you have diabetes, yes or no, right? And the independent will be the characteristics, right? Things that when it comes, it pops up, it's telling us that, oh, this person is a diabetic patient, this person is a diabetic patient, right? So at the end of the day, you see, we can use these two things to really help, right? So if we want to just check the correlation between these two, the diabetic patient, non-diabetic patient to be the dependent variable, and one of the characteristics like obesity, we want to check if the correlation between these two variables are very high. So if the correlation between these two variables are very high, it means that these variables are included in our analysis. Sometimes you will think that the correlation will be very low. There is some advice that you can transform the data, or you have to remove that variable from the data, right? So I don't the correlation variable in R. Once you run this one, right, you are just taking the first and the second column, right? So once you run it and just use the car function, the car here is what for the correlation, right? So correlation into bracket the variable the data name, right? So nicely. So once you run this one, it's surely going to come. So you write down, you see, correlation between the same variable is surely going to give us 1. Since correlation lies between 0 to 1 and 0 to -1, right? So from 0 to -1 is a negative correlation. From 0 to 1 is a positive correlation. So correlation between the same variable is going to surely give us 1 because it's a sure event. Correlation between that is surely going to give us since it's a sure event. So at the end of the day, you will see that the correlation between the distance and the speed is given as 0.06894. So this is it's a very, very high correlation between the distance and the speed. So this is telling us that, oh, these two variables are very good for us for it to help us in our analysis. So we have to include these variables inside our analysis. Sometimes you will test and it is very low. So if you test and it's very low, sometimes you have to remove that from the data, or you have to keep it in the data for you to be able to do your analysis nicely. Right? So that is the correlation analysis when you have a numerical data. Secondly, we have what we call a missing value in R. So in our previous videos, I told you guys how we can replace the NAs using the median or the mean, and we even plotted the histogram to get the median and then just replace it by our NAs that we have in our data, right? So the missing data, you see, for the inbuilt data that we are using, this data, I already told you that they are already prepared for our analysis, right? So since this data is already prepared for our analysis, what we have to do here is that we want to write a certain code, right? Write down small code. If we remove that missing data, if we remove the healthy data, right, to remove some part of the rows to do a missing data, so that we can use our KNN function to replace it by a similar, by checking the row and replace it by the similar number that I think it will help us in our analysis, right? So at the end of the day, for you to be able to remove this from the data set, just look here. You see, for the speed, all the data is filled. They are all 50. They are about 50 entries, and you don't have any NA inside. We are writing a code that will let it have NA inside, right? So that we can use it to do our analysis. right? So at the end of the day, you see we have remove rows. The remove rows here is just a function, a variable name, right? It's equal to what? The C function, that's this vector, right? So this vector is telling us we have 3, 5, 8, 9, 15, and 20. So this vector is going to remove the third, the fifth, the eighth, the ninth, the 15th, and the 20th rows in what? In the data, right? And then we just want it to remove it in what? The speed part, right? So we have what? The speed and then this, right? So since we have the speed and then this, we want it to remove it from what? The speed part, right? So for us to call our speed what column, we just use the data name dollar sign what? The variable name in the data, right? So here the variable name here is what? The variable name here we have is what? The speed, right? And then we bring our box bracket or square brackets with what? The remove dash rows. So the remove dash rows is what? This one that we want it to remove from what? Our data for us, right? So once you have this one, right, you just run it nicely, and then you are going to remove the row. So what you are going to tell us is that I have to replace this one, right, by what? N is, right? So once you run this one, once you run it and go back, you see, let's go back here. Come in, let's go back to the data. You see our N is has been removed from the data. Sorry, you see the third column, sorry, the row that we have that we commanded R to do, the third has been removed. The fifth two has also been removed, right? It has removed all the distance that we wanted him to remove. It has removed it for us. So now we are going to use what we call our KNN impede to what? Replace the NA by what? A number that I think that it will fix what our data. And in fact, this KNN impute is one of the best this thing to use for you to be able to replace NAs in your data, because for it's going to check the columns, the column wall, the individual values there, and then just predict that, oh, this value, when you replace this value here, it will help your analysis, right? More or less for the mean and the median. Sometimes they are good, but you see, when you check the number that KNN will supply or replace with the NAs and check the median, you see sometimes there is vast difference between the two, right? So for you to be able to use the KNN impute, what you have to do is that first you have to install what your current package in your data, and then also install what the RANN package in your R, right? So once you install it, then you just call it, right? You just call it, right? You just call, when you come to do the analysis, you just call this one, right? Then what you do is what? The impute that you can see here is just a variable name, right? So it's equal to the preprocessed function. So for the preprocessed function, the first argument that we have here is what? Our data name. So our data name will be what? Cars, right? And the method here is going to be what? KNN impute. We have other methods there too, right? So once you run it, right? Once you run this one, it will store in memory, and then you use the cars and they just predict the impute and the cars, right? So I don't know, you are just predicting, right, that I have to check what you have written here, the variable name. The first argument will be the variable name that you use to store the preprocess, and the second argument will do our data name, right? So after you are done, you see once I'm going to predict the number for you, and then we have this one. There's several for you to see that there is no NA in our data again. So once you follow that step, it's surely going to come, right? Surely going to come nicely. So this is what I have for you guys to try your hands on it. You just try your hands and see if it is normally distributed or not. When it's not normally distributed, just try to use the transformation that we just learned. The three, you use the log, the square, and the KNN impute. You try to use that, and after that, share it at the comment section for me to see whether you are right. If you are not right, I'll give you guidelines. So kindly watch the video well to get an idea about how things are moving in R. So for you to become a data analytics, you have to be someone who is well built in R and also know more about your machine learning. So these are the basics for you to know when you are handling numeric data. So this is Mathematics and Statistics Tutor channel. Please kindly like, subscribe, and share these videos to your friends so that they too can also benefit, right? God richly bless you for watching the video. Bye. Have a lovely day.